First, let me recall we said about scalar manifolds a little bit. So we had this triplet of structures. Omega always was related to the metric like this. G was orthogonal. It was an isometry. And of course, J squared is minus identity, complex structure. Right? And then we said it's scalar. There's several ways of saying it. One was the complex structure J is 0, or invariant equivalently pair translation isometry. Are complex linear. And this was if and only if the scalar form is parallel. And this was if and only if the scalar form is closed, plus J is integrable. Which remember meant that a certain tensor n identically vanishes the 9-house tensor. Okay. So all these things were a way of saying something is scalar. The simplest explicit example where everything is computable are again symmetric spaces. So I want to understand a little bit what do these symmetric spaces look like that are scalar in the sense. So we look at again a symmetric pair. We look at a Cartan decomposition. We identify P with a tangent space at my base point. And now I say, so definition, the symmetric pair is Hermitian symmetric. If the following thing holds, if there exists a complex structure J on the complement P, so it must be an isometry. J squared is minus identity. And it commutes with the adjoint of the isotrope representation. For all elements in the isotropic group. Remember, at K acts on P as my isotrope representation. So in other words, at K is complex linear. Or if we want to add the image of at K restricted to P lies in the unitary group.
Complex structure is defined in all?
Only at P. Right? Only at P. I'll define it on the manifold a little bit later. Right now, it's just an algebraic concept at a point, right? So I have my Cartan decomposition. P I can think of as a tangent space if I want to, but algebraically it's just my composition P. Remember, at K takes P to P. So I have this representation on P, right? And on this vector space, I want a complex structure which respects the matrix, orthogonal, and commutes with at K. That's the only thing I have right now. And now I want to construct from this a scalar metric.
I was thinking that you want to require that G to be complex.
No, no.
You don't need it.
You don't need it. In fact, G will not be complex Lie. For example, there are compact Hermitian symmetric spaces, in which case the G is the compact Lie group. Right, so there are natural examples where it's a compact Lie group. And of course, compact Lie groups can be complex. Right? But we're going to see that this complex structure is actually integrable, and G acts via holomorphic transformations. So that's the relationship, right? G consists of holomorphic transformations. And then if I complexify, I get the set of all possible holomorphic transformations.
Yeah, related to this, I've heard something about any compact Lie group, connected compact Lie group, can be embedded in UA.
That's just yes. Up to covers. So there's some cover or some G mod gamma, say, up to covers. There's some G tilde related to it. So let me just call it G. With a unitary complex representations. That's what it means. So every compact Lie group has a unitary complex representation. And then it may have a kernel. If I divide by the kernel, I get another Lie group up to covers, and it's then embedded into UN. That's true. Okay. Of course, UN is not a complex Lie group, right?
Yeah. But any, I don't know if simple connect complex Lie group is the complexification of some real Lie group?
If it's semi-simple. In general, it's this question whether a complex Lie algebra has a real form. Right, so if this is true, certainly the complexification of the Lie algebra must be the given Lie algebra, and not all Lie algebras are complexification of something. But if the Lie algebra is semi-simple, then it has a real form. Then it's true. Okay. In general, not. Okay. Yeah.
Why is that K restricted to be all of UN?
Oh, sorry. It's contained in UN. Thank you. That's of course not. That's usually not true. Sorry. It's complex linear, and it's an isometry. Of course, isometry was required as you want to get a Kähler metric, so certainly you want to do isometry. And that's what we want to claim now. So proposition G, K Hermitian symmetric implies G is Kähler, and G acts by holomorphic transformations. On G mod K. Right, with respect to the complex structure I'm going to define on the space using J itself. Okay. So let's prove this. So we have this general principle that we already saw several times. If I have some tensor or some object at my base point here or P equivalently invariant under I-stop representation, I can push it around and make it well defined on the whole manifold. So I want to define the complex structure on G mod K by J at the point GP. So I push around the left translations, right? So clearly, is that a question?
I don't remember if in the definition of symmetric pair we require G compact. No.
Required to be almost effective was one condition, right? So the Lie algebra K and G only have a finite subgroup normal, but not compactness, right? But one consequence was that if it has no Euclidean factor, it's semi-simple. But it can be compact and non-compact. Okay. So this is how I would push around a tensor, right? And now clearly if I square this, I get minus identity again. So when I square this here, this cancels, and J squared is minus identity. So this is a complex structure on the tangent space at GP. And then this is well defined. Maybe by Buser notation, I'm using the same letter J here. G is well defined since J at the foot point P naught is at K invariant. Right, so if I can write J GP as J G prime P possibly, if GP is equal to G prime P, right, then G prime inverse G is P is equal to P, so that's equal to K. So the usual argument we've seen already, right? So that means that G is G prime K. Right. So left translation by G is left translation by G prime composed left translation by K. And this key is a complex structure invariant. That means no matter which one I left translate with, I get the same complex structure. This was our usual argument. Okay. So that's the complex structure. Now I need to show, for example, that it's parallel. This here would be one way to see it's scalar. For this, let's look at the following. So outside the symmetries, for my symmetric space, which has symmetries, at the point, let's do it at the point P naught. P naught was my chosen base point. And then I want to look at a new complex structure. Let me call it J bar, say, which is pulled back with my symmetry, the complex structure J. By pullback, I mean the usual thing that one talks about when I do a pullback is the same thing I did over there. Just like I pull back forms, right? I can pull back any tensor, and that's what I mean by that. So I claim that J bar is again a complex structure. Right, that's clear. If I square J, this cancels in the middle. J squared is minus identity, so I get minus identity again, just like over there. So I have another complex structure, which comes from a complex structure J. And now the claim is that J bar and J are left invariant. And so let's assume this claim for a moment. Then how do I finish? If I have that, then notice that J bar at the foot point P naught is equal to J. Right, the foot point P naught. The derivative of this map is minus identity. These cancel here, and I get J. If I know both are left invariant, they agree at one point, that means they agree everywhere. So in other words, the symmetry preserves the complex structure J that we've defined over there. And now I could say, now I can finish in several different ways. For example, I could say hence sigma P naught star preserves the nine-house tensor N for the complex structure that we defined on Tuesday. And remember, this was a 2-1 tensor. Right, I plug in two vector fields, I get a vector field out. Invariant of the symmetry, therefore it must be 0. Okay. That's one way to see that again. Odd tensors vanish if they're invariant of the symmetry. Or another way to see it would be to say, sigma P naught, because it preserves the complex structure here. Sigma P naught also preserves omega. Right, omega xy was jxy. So I'm defining it that way, right? Here on my complex structure J, I just defined it globally over here, so now I have a corresponding form. Right? And now Jp naught preserves J. Of course, it's also an isometry, preserves a metric. This implies that sigma P naught star omega is also equal to omega. Okay. Of course, omega has even order, right? It's a 2 form. But there's another tensor of odd order associated to omega. It's co-derivative. Right here, this implies that sigma P naught star also preserves an upper omega. Of course, it's an isometry, right? So it preserves isometry, preserves Levi-Theta connection, and therefore also the co-derivative of my invariant form. And again, now, this has odd order. Invariant under the symmetry must vanish. Okay. So I wouldn't have to go over the Nine-house tensor. I could also argue directly with the corresponding Kähler form. And one of our definitions of Kähler was that that's Kähler. Right? So maybe that's an easy way to see it. So that would be the proof, and all we have to see is this claim here. So let's see. We defined, J was defined as, at GP, was defined as LG star of J, let's say at the point P naught, right? So our J in the theorem, I can regard as an element at P naught, taking P naught and P naught M. Just to have some way to differentiate. So that's my J, and now I want to take sigma P naught star of J. I want to prove it's left invariant. Right, that's my compact structure, which I also want to claim is left invariant. Clearly, J is left invariant, right? So this is by definition left invariant. I define it by left translations. Right? So I have to prove this one's left invariant, and J bar was just the pullback of J under my symmetry. So apply LGs to it. Pull back with LG. I want to show it's equal to J to say it's left invariant. Well, so this is LG composed with the symmetry at P naught star J. And I claim this is the same thing as a symmetry at P naught composed with L sigma of G star J, where sigma was my symmetry, which is always for my symmetric pair. Right? And of course, this is then now sigma P naught star of L sigma G star J, but J was left invariant, so that's sigma P naught star J. This is what I call J bar over there. So indeed, LG star of J bar is equal to J bar. It's left invariant. Here, for this step right here, where is it? This is an equality that we've seen before, so I claim general fact was LG composed with symmetry at my base point is symmetry at the base point composed with L of sigma of G. So we've done that before. You just plug into the coset, just verify it on the cosets. And remember that the sigma, did I mix up sigma and S? Okay, I mean, in the notes I usually call this SP naught, but okay. I'm not going to change it now. So here you have to remember that sigma P naught acts on, say, a coset as sigma of H times the coset, where sigma is the automorphism. So yeah, this is really bad notation. So sigma and sigma P naught are different things. Sigma is the automorphism, and this is the symmetry of the symmetric space, what we call SP naught. So that's what the sigma P naught looks like in the set of cosets. Then if you plug in, you just get this equation. That's what I used right here. Okay, that's it. So I proved my claim. They're both left invariant. They agree. Invariant of the symmetry, and that has strong implications. So you need very little to make a symmetric space into a Kähler manifold, right? Just the complex structure at one point. Or to say that at K, the isotope representation is complex linear. That's all you need. Right? Then you get a Kähler metric out of it. Okay, so let me prove some simple properties of our Kähler manifolds. Well, maybe first the corollary.
If we have that K is compact, do we construct always such a complex structure?
The symmetric space could be odd-dimensional. Or if I look at even dimensional, right? Look at a sphere. Well, that's even dimensional. So this will be as odd dimensional. This will be as 2n. That's a symmetric space. That's a symmetric pair. It's even dimensional, right? But this is not a Kähler manifold. In fact, there's no compact structure which is preserved by the action of S or 2n. So here, if you think of the isotrope representation, Atk is just the standard representation of S or 2n and R2n. That's the action of Atk for the symmetric space here. And the claim is there's no compact structure on R2n which commutes with the action of S or 2n. Can't be because un is much smaller than S or 2n. Right? So it can't possibly exist. So it's really a condition, a strong condition.
We can find a complex structure such that it's an isometry, but the problem is the
complex linear, absolutely, exactly. If it's even dimensional, certainly there exists such a J which is orthogonal, absolutely. But to commute Atk is an important thing. Of course, that's what enabled me to define it, right? That's exactly what I need to define it globally. So it's natural that it should have that property. Right? If there's any chance to find something G invariant, it must have that property, and that's all you need. That's what the theorem says. Okay. I noticed the last part here that G acts by holomorphic transformations is by definition, right? G acts by a left translation of my space. And the compact structure is left invariant. So left invariant transformations preserve the compact structure, and that's why it needs to be holomorphic for this integral complex structure. Right? It's now a complex manifold. These are holomorphic transformations. Okay. Another one, corollary also. M Hermitian symmetric plus irreducible implies a matrix Kähler-Einstein. That's the first property, and the second property, M Hermitian symmetric, implies that the dual M star, in the sense of symmetric spaces, is also Hermitian symmetric. So for A, I just combined with what we've seen before. Remember, an irreducible symmetric space means that Atk acts irreducibly on P. That means the Ricci curvature and the metric must be multiple of each other because they were both invariant under Atk under this irreducible representation. So that means it's Einstein. That's what we discussed before. Irreducible symmetric space is Einstein, and we just saw it's also Kähler. So it's a Kähler-Einstein metric. So among Kähler metrics, the ones which are Kähler-Einstein are the most important ones. It's an important question, which Kähler manifolds are Einstein metrics. And some of the simplest examples of Kähler-Einstein metrics are indeed these symmetric spaces. We'll see some examples in a minute. So to construct in this form, one thing I would have to do, which we really haven't done, is I would have to complete explicitly what is the isotropic representation of my symmetric pair. We've written down lots of symmetric pairs, but we usually didn't compute the action of Atk on P. Then I have to take a look at that and see whether it's complex linear. But that's how I would check that a symmetric space is Hermitian symmetric. But there's an easy way to do that. In fact, there's an amazingly simple characterization of which symmetric pairs are Hermitian symmetric. I can say it in 3 different ways. Let's see. A, G mod K is Hermitian symmetric if and only if, do I need to assume something? Irreducible, symmetric pair, irreducible. But remember, this is not such a bad assumption, because if it's not, the universe's cover is an isometric product of irreducible ones. Right? So understand these is really all I need. If and only if K is not semi-simple. So that's one characterization. If in addition G mod K is compact, then it's summation symmetric. If and only it's the second Durham cohomology, or the manifold is non-zero. Again, that's a natural condition, right? A Kähler manifold is a symplectic manifold. That means the Durham cohomology class over omega is something non-zero in here, right? So certainly this group must be non-zero for there to be a Kähler manifold, which is compact. Which is compact. But that's sufficient. That's all I need to make it into a Hermitian symmetric space. K is equal to K prime times S1. So remember, K is not semi-simple. Particularly, that means that if I say look at the Lie algebra, if it's a compact Lie group, right? So the Lie algebra is compact. If it's not semi-simple, it must be a product of a semi-simple one with something abelian. Right? That's the only way a compact Lie group cannot be semi-simple. So here, this is what I'm saying here with. So I mean, again, this is not so unnatural with K prime semi-simple. And compact structure J, so I can write down explicitly what it looks like, is at of I, where I is a unique element in S1 with square minus identity, minus 1. So without doing any computation of what the Ice representation is and what are the possible compact structures, I can write down explicitly. It's this one. And there's only one particular. Right, if I can make this into a Hermitian symmetric space, the compact structure is unique, and you can write it down right away, just knowing what K looks like. So let's do some examples. But we can just now look at the list. Look at the list of. Yes? What? I can just now look at the list of symmetric spaces and see in which case is K not semi-simple. That's all I have to do. So, examples. Do you remember somewhere K is not semi-simple?
Not semi-simple.
Pardon?
Not semi-simple.
Not semi-simple. Right. But G is from being an irreducible space. G must be semi-simple, right? This was a consequence. I guess symmetric pair irreducible and not of Euclidean type, so not flat space. I always make this assumption, otherwise it's hard to say anything. So G is semi-simple, and it's a question of whether K is semi-simple or not, whether K has a center. And if it has a center, the center must be one-dimensional. In fact, here maybe I can add to this the center of group K is actually equal to S1 if G mod K is effective. The center is a circle. It could be across another finite group or something a priori.
Wolfgang, would you say again why we call that G is very simple?
Okay, so symmetric pairs which were irreducible there were three categories, right? Compact type. What does that mean? Whether the killing form on K is negative. Compact types means on P it's also negative. And we always had that K and P were orthogonal. So it's non-degenerate, the killing form. Right? Non-compact type, this here was positive, but still orthogonal here negatives. It's again non-degenerate. Okay. So I have to exclude the Euclidean type because on that P the killing form was 0, so certainly it's not semi-simple. Right? But it's not a big deal anyway, as we know.
UN is not semi-simple.
Pardon?
UN is not semi-simple.
Correct. So what was the symmetric space where K was UN?
The gross magnitude.
Grassmannian.
complex.
So SUN mod S of U K UN minus K. So Grassmannian of K planes in Cn. Of course, it has to be a complex manifold, so it has to be Hermitian symmetric. And here, of course, this here has a two-dimensional center. It's 1 causes 1, but I take those with determinant 1, so it's a one-dimensional center. Okay. What's another one?
No, I was thinking really of the complex structures. But it's
What they look like, you mean?
what?
Say that again?
The SO4 under U2.
Yes. More generally, SO2n mod UN. And the set of complex structures is a Kähler manifold.
Orthogonal complex.
The set of orthogonal complex structures is a Kähler manifold, right? Center is one-dimensional. Another one?
Some Gaussian with SPN.
Yes, SPN mod UN.
What does it represent?
I forget right now. What was that again?
Some kind of quaternionic structure.
Yeah, it's a, I think,
Complex structure.
no, it's a structure on Cn, like multiplication by J, kind of, right? So it's a complex antilinear map with square minus identity. And if I think of multiplication by J, it's complex antilinear, squares minus identity. If you want, it's a way of identifying C2n with Hn. But to do that, I have to know what does J look like. I know what I looks like already. And J on here is a map whose squares minus identity and is complex antilinear. And that's what this looks like, a set of all such structures. Very important thing for representation theory. It's how can I decide whether a complex representation is a quaternionic representation by these kind of structures. Okay. So I didn't talk much about that because we didn't do representation theory. Another one? A simple one. How about real Grassmannians? Any real Grassmannian where the K is not semisimple? So it's SOP plus Q mod SOP SOQ, right? Is that ever not semisimple?
What was the complexification?
SLNs of SOP, SONC. So the question, when is SONC semisimple or not? So SN is semisimple except for a stupid case. SO2. That's not semisimple. So take SON plus 2 over SON SO2. So the real Grassmannian of two planes in Rn plus 2. So here there's a one-dimensional center, that's this group right here. So it must be a complex Grassmannian. This is often called a quadric. Very basic example of a complex manifold that occurs in many contexts. So each set of two planes in Rn plus 2 has a natural complex structure on it. And then there's a classification which claims that this list is complete plus two exception ones, and that's it. You see, I wrote them down. Yes. So just for completeness, I write them down, not just going to discuss them. E8 mod spin 10 times U1. And E7 mod E6 times U1. That's a complete list now. Okay. So these 4 classical ones, classical Lie groups, and then 2 with these kind of nasty exceptional Lie groups. So this follows after classifying all symmetric spaces and then checking when is K semi-simple or not. That's the proof. Okay. Okay, so let's prove this. Actually, this is fun to prove.
Why was SO1 and SO2 not semi-simple?
Because SO2 is not.
What?
SO2 is a circle. It's a abelian.
I cannot have any center.
Pardon?
Because we cannot have any center.
There must be a one-dimensional center, right, for the full group K. So the full group K here is SON times SO2. And SO2 is a circle. It commutes with SON, so it lies in the center of K. Right. Now it's criterion. K can't be semi-simple, which meant, and in fact, it has to have a one-dimensional center. But certainly this group is not semi-simple because SO2 is not. Yes, they're actually all if and only if statements. But I can just use A, right? SO2 is not semi-simple. It's not, yeah. SO2, by definition, wasn't semi-simple. Okay, so SON cross SO2 is not semi-simple either, and then by A it's a symmetric space. But by C, I should kind of expect that there's only a circle that splits off. Well, how does that fit with the example we discussed in the beginning? There was SO4 mod SO2 SO2. That's certainly not semi-simple, but it's abelian. So S1 crosses 1. So that doesn't fit C. Why is that? So it's certainly Hermitian symmetric because K is not abelian. That's what A says. But C says, in fact, there should be only one-dimensional center. There was an assumption in the theorem. It's not irreducible. As we just discussed, this S2 causes 2. So it's a product of 2 irreducible symmetric spaces. So for part A, I don't need it. It doesn't matter, right? K is not semi-simple. That's sufficient. But if I want to say the center is only one-dimensional, then it should be irreducible. Otherwise, it doesn't hold. So here, actually, for part A, I don't even need irreducible. In fact, irreducible is only used in C. So maybe I'll just state it that way, right? The symmetric pair with no Euclidean factors. Maybe that's the best way to state it. Take any symmetric pair with no Euclidean factors. A and B always holds, and C holds if it's irreducible, an irreducible Hermitian symmetric space. So to prove this, we do B first. So we're looking at Durham cohomology. I think along the proof, I probably have to use a few things that you may or may not know. Okay. So one direction is for B is clear, right? So if I know it's Hermitian symmetric, then the Kähler form is non-zero in the Durham cohomology, just because it's symplectic form. So let's try to do the converse. So take a non-zero class, take a form, two form, whose Durham close two forms. So I know right now that D omega is 0. I don't even know that omega is not degenerate. It's not clear yet. There's some class in here which doesn't vanish. So a closed form in here doesn't vanish. I want to construct from that a complex structure. So, and in the end, omega will have to be a symplectic form. So the first thing I do is I claim that I can average forms. I want to make omega G invariant. So how to do that? I integrate. So here I'm assuming M is compact, right? So G is compact. So this part of the conclusion is that G is compact. So I can average over G because my Lego is compact. Right. So now I claim the following. So claim A omega is G invariant. That's kind of clear, right, as usual. If I average something, it's something invariant. B, d omega tilde is also closed. And C, the cohomology class of omega tilde is the same as the cohomology class of omega, and hence non-zero. Okay, I can just replace my de Rham cohomology class with something that's invariant. This is, in fact, a very general principle. I mean, as take any manifold, take any compact Lie group act in the manifold, transitive or not, doesn't matter. These kind of properties always hold that on a compact manifold, that I can replace a de Rham cohomology class with one that's invariant under the action. Well, so for example, why is so A is clear? Why is B true? Well, D commutes with the integral. Well, I can say that's the same thing as integral G d of G star omega. And D commutes with pullbacks. So it's the integral of G star of d omega. Of course, omega was closed, so it's also closed. So the average of this form is automatically a closed form by the properties of the exterior derivative. Now I just want to say it has the same cohomology class. Notice that since G is connected, left translation by G acts trivially on de Rham cohomology. Right, they're all non-homotopic. They're all homotopic with the entity because G is connected. So it means the action on the de Rham cohomology must be trivial. So this says that the cohomology class of all these pullbacks is the same. It's always equal to omega. So now I average something that lies, so all these things lie in the same de Rham cohomology class, I average, and then this also lies in the same de Rham cohomology class. That's kind of neat, right? In de Rham cohomology, I can average. In fact, one can.
Up to a factor or divided?
No. Oh, okay, so let's. Here it doesn't matter, even not up to a factor. Why up to a factor? So here I'm using the fact that this is the same thing as, oh, sorry. It doesn't matter. Are you worried about that? The integral of the volume is equal to 1. We often normalize like this. In this case, it's probably not even that important. But sometimes it is. So very nice general principle, right? Take a form, average, it's still a form, the same de Rham cohomology class, as long as G is connected. And G is not connected, then I could even get something zero, like take a form on the sphere, say the top volume form of the sphere, average under SON. Well, SON preserves it. Of course, it's the same thing again. Average under ON, and then it becomes 0. Right? So in general, when I average over a group, I might even get something 0. This thing could be 0 in de Rham cohomology, because the action might be non-trivial.
How did you explain the last application there?
So I knew that LG is homotopy to the entity, because G is connected, a connected entity. This implies that LG star of omega has the same geometric cause as omega for all G. And now I average. So I stay in this cohomology class for all G. I average, so I integrate over G. This also must have the same cohomology class, because I'm not changing it. Okay? You can continue and say that, I can look at the subalgebra of the Durham complex, which consists of those forms that are invariant under any compact group action on my space. That's a subcomplex. D preserves it, the wedge product preserves it. I can look at its cohomology. That's the same thing as the Durham cohomology. Okay. Particular, for example, if manifold is homogeneous, I can reduce the whole thing, computing Durham cohomology, to a linear algebra problem. Because then I know the form is determined by the value at a point, or complement P usually. Right? So form is just something on P. Invariant under I star representation, to be well defined. So I look at that algebra, that's a fine dimensional algebra, and look at things that are, so G invariant on M would be at K invariant on P. So I look at the algebra, so maybe you can write it like this. Right? Durham cohomology of G mod K. Look at the algebra of P, and look at things that are at K invariant. Okay. Or the complex, so actually in general there could be a differential on there. Not everything is closed in here. But at least this is something fine dimensional I can compute. And then I compute its cohomology, and that's the Durham cohomology of my space. So for homogeneous spaces, one can compute this. Where were we? We wanted to prove its emission symmetric, so we have to construct a compact structure. We took a form, we average, we have an invariant form, and I claim that's my candidate for my Kähler form now. So I have omega, now I also have my metric. Right? I can define the compact structure the way I want it to be. I want this relationship to hold. That's well defined because this is a metric. Right? This is a bilinear form. Therefore, I can write it as an endomorphism times a metric. Right? Of course, J could, right now I don't know anything about J yet. I'm not saying it's a compact structure. Could even have a large kernel. I don't know, it's not degenerate. I don't know very much yet. But I certainly can define J in this fashion. What's the next thing I can say? Okay. The metric and omega are G invariant. So let's say my J here I just defined as an endomorphism from P to P. For emission symmetric space, all we have to construct is some endomorphism P to P. Let's just do it on P by this equation here. Okay. So the metric and omega are G invariant, which means that hence J is at K invariant. Right now, I made omega G invariant, so maybe I call it omega tilde there. Let's say omega is my G invariant form now, which exists by assumption, not construction. Of course, GX by isometries, I have a symmetric pair, right? That was my starting point. I have a symmetric pair, GX by isometries, so therefore this is true. So in other words, I can say J composed with at K is at K composed with J. So what does that mean? at K acts irreducibly on P. So maybe I'm using it now in that place also, I suppose. Although it's not so important. At K acts irreducibly on P. It's injective. It's even onto. It's an isomorphism. Because at K it's reducibly. It's one consequence. Because the kernel or the image would be at K invariant, and therefore it must be 0 and everything. Because I want more, I want it to be a complex structure. In this generality, it doesn't have to be yet. Also, what do I know about J? I only know at this point from this equation here that J is skew symmetric, so it's what is that? Skew adjoint. Right, omega is skew symmetric, so I have we've done this computation before. That's omega yx. Definition, that's jyx minus, and that's then minus xjy. So J is a skew-symmetric anamorphism. It's not even orthogonal yet. I don't know that either. But now I can do the following. I think we had this discussion once before. It's an endomorphism that commutes with an irreducible representation. So I think the first guess that someone made at some point, well, that means it's a multiple identity. But that doesn't have to be the case. In fact, for a Hermitian symmetric space, certainly it's not the case. Complex structures are not a multiple identity. That was true over the complex numbers. For a complex representation, that was true, not for a real one. But I can do the following. I claim that J squared is symmetric or is self-adjoint. If I take a skew symmetric, its square is symmetric. So skew adjoint is self-adjoint. Because it also commutes with at K. What does that imply? It is a multiple identity. Lambda times identity. But it's not clear yet whether it's plus or minus 1 or whatever. It's just some number, some real number. I don't know yet that J is an isometry either, so I can't use that either. But I can say that lambda is negative because J was skew adjoint. Remember, a normal form was skew adjoint matrix like this in some basis. And its square is minus a squared, 0, 0, minus a squared. So that means if I choose such a basis, it must be a negative on the diagonal. Since multiple identity, it must be negative multiple identity. So right as a square.
We divide by mu?
Divide by, absolutely. So J tilde is 1 over mu times J. And then, of course, J tilde squared is minus identity. Right, it's 1 over mu squared. Mu squared is, J tilde squared. 1 over mu squared, which is 1 over lambda. And J squared was lambda identity. Okay. It's a complex structure, and also J tilde is orthogonal because it's skew adjoint and it's a complex structure. So remember this discussion, if I have a matrix, say, where A is minus A transpose plus A squared is minus identity, this implies A times A transpose identity. It's orthogonal. Okay. So the J tilde, because I made it into a complex structure, and because it's skew adjoint, is orthogonal also. Now I'm done. Right? I have my complex structure on P here, my J tilde. I normalize it so everything works out. Right? It's commutes at K by construction, right? And that's all I needed. At K is not complex linear, therefore it's a symmetric space. That's kind of neat, right? A very weak condition on Durham cohomology, and you already get a symmetry space out of it. What should I prove next? Let's see, something that's fun. Oh, maybe A. I think A is kind of fun. In fact, that's what we used in order to construct examples, part A. So let me do that. Here I have to also use some facts from topology that are nice, that you may not know. Okay. What do I know? G is semisimple, right? Plus compact. You may remember this implies that part 1 of G is finite. But a semisimple Lie algebra has no center, so the Lie algebra G has no center. That means the center of G is discrete. But if G is compact, a discrete group must be finite. So part 1 of G is finite. What next? So this implies claims that part 1 of M is finite. Because remember, I have my vibration. G goes to K goes to G, goes to G mod K. And here I have pi 1 of G goes to pi 1 of G mod K, goes to pi 0 of K. K is compact, has finitely many components. That's a finite group. This is a finite group. Therefore, this is finite also. So I can look at the universal cover. And M tilde is still compact. Okay. And
But in our case, because of being Hermitian symmetry, is it compact?
Say it again?
Do we have G compact?
Yes. Because, okay, let me see. Good point. Absolutely, good point. So, initial step, reduce it to that case. Because, by duality, right, you see it's irreducible. It's either non-compact or compact. K is always compact, but G or maybe not a non-compact. If it's non-compact, take the dual. That is compact. And they have the same K. This is a statement about K here. So I might as well assume it's a compact type. Like you're right, of course, that's, so assume of compact type by duality. So M tilde is compact. How does the Durham cohomology of M tilde, of M and N tilde relate? Do you know that? The map is injective, yeah. You even say more than that, so that's enough for me. The map is injective. But the exact relationship, do you know what that is? What do you want to do? You want to take a form on M, pull it back to M tilde. That's a form there also. It gives you a possible Durham cohomology class. It must be invariant to the deck group because you pulled it back from something. So in fact, it's simply the forms, the things invariant to the deck group. Then I get equality. Okay. That's a nice exercise. In our case, all I need to know is that the second Durham cohomology M tilde is also non-zero. Which means that pi 2 of M tilde is non-zero. then tilde is simply connected by Hurewicz. Right now I'm using Hurewicz. Pi 2 is isomorphic to H2. For a simply connected manifold.
Why?
That's called Hurewicz. In general, if you assume there's if you look at the first couple of homotopy groups of your space, you go up to this space where it's first non-zero. That homotopy group is isomorphic to the corresponding homology group. So first, as long as homotopy vanishes, homology vanishes. First time they don't, this group agrees with this. That's a theorem. It's called the Hurewicz theorem. That's an important theorem. Have you seen that? It's in Hatcher, yes. If you do some topology, one of the things in Hatcher. So pi 2 of m tilde is non-zero, which means what? Pi 2 of m tilde is pi 2 of m. Right, because this is a finite cover. Under covers, the higher homotopy groups is an isomorphism on the higher homotopy groups. I'm using a little bit of topology. And now what does that imply? Now I look again at my fibration here. So I write down pi 2 of g to pi 2 of g mod k to pi 1 of k to pi 1 of g. So what do I know? This group is finite. This group is non-zero now. And now I have to use a theorem that this is zero. In fact, every Lie group, period, every Lie group has vanishing pi 2. That's a nice theorem, non-trivial. You can reduce to the compact case by saying that, well, every Lie group is diffeomorphic to its maximum compact subgroup across the Euclidean space. It's the same thing as saying every Lie group is diffeomorphic to its maximum compact subgroup across the Euclidean space. That's a theorem that one can prove. Again, it has to do with symmetric spaces.
And the compact one has a complete metric.
Yes.
And we have a surjective, the tangent space for a point, and the exponential is surjective.
Yes.
And isn't that a covering?
No.
No.
When is the exponential recovering when you measure geometry?
So the metric is not preserved, that is not
For the sphere, for example, on the sphere it's not occurring. If the curvature is non-positive, that's the theorem of Hadamard, then the exponential is occurring. In general, it's not. Right? So, not that easy. There is a geometric proof. So it's a compact Lie group. It has a bi-invariant metric. Then what you can do, you can use Morse theory. You look at the Morse theory on the loop space of your Lie group G. And if you look at Milner's book, he does one application of Morse theory is Morse theory on a loop space of a manifold. Since G has a bi-invariant metric, you can either compute everything. You can compute Jacobi fields. You can compute conjugate points. And you prove, just by looking at the conjugate points, that they are of even order. So all indices of these critical points are even. That means that there's no differentials. All the homology occurs in even index, in even dimension. And that means that pi 1 of the loop space is 0, which then means pi 2 of the group itself is 0. That's an outline using. But what I'm saying is there's a very nice geometric proof. Using the geometry of the bi-invariant metric, we know its curvature. We know what geodesics look like. You can compute Jacobi fields in terms of Lie brackets. And then for that, you can compute the index of a geodesic. So everything's computable. And then you use Morse theory.
Once you have it for compact groups, is it easy to generate?
No, not quite. So you have to prove that, so if you have an arbitrary Lie group G, then there is a maximum compact subgroup. It's actually unique up to conjugacy, and G is diffeomorphic to K across some Euclidean space. That's a theorem. Okay, but it's not trivial. So then you reduce it to the compact case, and then you use geometry on the loop space of the compact Lie group. Okay. What does this imply? Okay, now we have this is 0. This is non-zero. In fact, this contains at least a z. Right? So this Durham cohomology group is non-zero, so it contains at least an r. That means the integer homology must at least contain a z. So this contains a z here. But because this contained a z, right? Durham cohomology is this here. This contains an integer. Therefore, this does. That's what this. So it contains the integers. So this must also contain, this one can't be finite. Pi 1 of k is not finite. Okay. But if k was a compact semisimple Lie group, pi 1 would be finite. So therefore, it cannot be semisimple. That's the proof of this. So kind of neat combination of a little bit of geometry and a little bit of topology. Okay, I don't think I'm going to prove this one here. It's my notes. I want to go on to the next subject. I think this is all I'm going to say about Hermitian symmetric spaces. I can say a lot more, which I do in my notes. They're always simply connected. There are many things one can say about Hermitian symmetric spaces, but it's my notes I want to do here. What I want to do next is the holonomic groups. Remember, the next set of holonomic groups are SPn, SPn times SP1 in those. So having to do with the quaternions. So I want to discuss the geometry that has to do with that kind of holonomic group. So these are called quaternic manifolds or quaternic Kähler manifolds. I want to discuss those, and again, then the main examples are the symmetric spaces which have that structure. So there's certain analogies, which what we did for the Kähler and Hermitian symmetric spaces, also in that context. Now I want to do it next week.